All right, let's take some time to practice these types of reactions. I want you to predict the product with the mechanism. So maybe you can pause the video, think about these, and then unpause, press play, and we will work on them together. The first question gives us a secondary alcohol reacting with HBr. And we know, again, this is a poor leaving group. What we're going to do first is to protonate the poor leaving group with the hydrogen. I'm going to switch colors here just to make it a little more interesting. I'm going to draw in the HBr bond and show the Br leaving. Now I've protonated my OH. I have water here. I also have Br. Because we are in strongly acidic conditions, it's likely we might form a cation here. So I would propose that we could get cation formation. And because we have the opportunity to rearrange, we might form tertiary cation. And here the bromine can add as a nucleophile, bringing us to here. This molecule is not chiral, so we don't have to draw both enantiomers in this case. We could also have the bromine react with the secondary cation. It's much less likely because that secondary cation probably does not exist for very long, but that would be another possibility. This is probably the major product here. Let's look at the second option on this page. We've got a primary alcohol reacting with HBr. So the first step, again, protonation of the alcohol. Now we have water as our leaving group. That's not going to leave on its own now because we're on a primary position. But if I take the bromine and I use it as a nucleophile, I can push water off while creating the new carbon-bromine bond. And that would be the product I would expect here. The bromine has substituted the OH to make a primary alkyl bromide. Some more options. This question here gives us a tertiary alcohol reacting with concentrated H2SO4. The first thing we'll do is, again, understanding that we have a small amount of hydronium present. That will be the most common acid, most likely to protonate the OH in this process. There I have protonated alcohol. I have a tertiary position. I'm ready to lose the leaving group, leaving behind a cation. And you should be able to tell me why this cation is even more stable than the standard tertiary cation. Hopefully told me it has some resonance structures, and it would be great for you to draw these resonance structures as part of your mechanism here. So one of them would probably start from that red arrow, and then you could draw some more. So we have this tertiary cation. We have some beta hydrogens that we can eliminate. I didn't mean to use blue there. Beta hydrogens that we can eliminate, giving us some alkene products. And is there stereochemistry associated with this alkene? I think there is. We should draw the other version as well. I drew the E version there. Here is the Z version. And there's another beta position as well, isn't there? Let's use a different color here to show that beta position. If I use the water to remove the beta position, or the other green beta hydrogen, I might produce an alkene that looks like this. Are there any stereochemical issues associated with this alkene? It's at the end of a chain. It's a terminal alkene. I would say there are no stereochemical issues associated with it. So which of these would be the major product? It should be the most substituted alkene with the most stable stereo configuration, and that would be the first one I drew. So the major product would be up here. It's always important for us to identify the major product. Everything else would be minor in this case. We're not going to concern ourselves with the specific amounts of each of these, just that one is the major and two of them are minor. So again, this would be a dehydration, an E1 mechanism, dehydration. Concentrated sulfuric acid plus alcohols often lead to dehydration reactions. We'll experience one of these in lab this semester. Lastly, we have some tosyl chloride and pyridine as our first step, strong base, strong nucleophile as our second step, and we have this secondary alcohol that we want to use as our starting material. So the first thing to do is to turn this into the tosylate. Again, that mechanism is not going to be covered this semester, so as long as you can show me that we've created the tosylate from the alcohol, I'm happy with that. So now we have a good leaving group. This is a secondary substrate. I've got a strong reagent here. That should lead to E2 as the major product with a small amount of SN2. And so I now have 2 beta positions here. And let's go ahead and lose HA using our nucleophile. That's loss of HA. Is there any stereochemistry associated with this? Indeed. I could draw the Z version. So this is minus HA. The other regioisomer then comes from loss of HB. And I'm sorry, I forgot to show my loss of leaving group. This is an E2 mechanism, so there are going to be 3 arrows. Loss of the last loss of leaving group, of course, is important. Same with this green mechanism that I just drew. In this case, we have this regioisomer with the alkene forming on the less substituted side. There is no stereochemistry associated with here, so this is the only isomer we'd expect from loss of HB. And last but not least, of course, there's a small amount of SN2 chemistry that we might expect. Push off the leaving group in our standard SN2 process. This would give inversion. So the stereochemical outcome here is a change in the designation of that stereocenter. This would be the only option for substitution. So I think that would be another minor product. So this would be minor. This is minor. This one would be minor because it's the less stable of the alkene products. And this would be the major product that we'd expect because it is the most substituted and the most stable of the stereoisomers of that alkene.